And the only talk today in this session left is by Nina Balcan from Georgia Tech, who will be talking about distributed machine learning.
All right, thank you, Thomas. So this talk is about distributed machine learning, and in particular, I will be talking about a theoretical model that we have been developing for reasoning about key issues and resources appearing when we want to do supervised learning in distributed settings. Okay? And since this is a little bit of a broader audience, I will, in terms of the structure of my talk, I will start by giving a very quick, high-level overview about the usual way to analyze supervised learning in the classic centralized setting, and then I will present our results. Okay? So as probably everyone here knows, supervised machine learning is one of the most well-studied or understood topics in machine learning. So in this setting, the learning algorithm would use labeled examples. For instance, email messages labeled as spam or not spam if our goal is to do spam detection. Okay? And for this setting, there are two very nice general and closely related models, in particular the statistical learning theory framework of Abnick and the PAC model of Valiant. And in these models, we assume that there exists some underlying probability distribution over the space of unlabeled examples, for instance, over the space of unlabeled email messages. And then in the training phase, the learning algorithm first gets to see, in the training phase, we first get to see a random sample from this distribution. This sample is then labeled by an expert, for instance, spam or not spam for the spam detection problem. And this set of labeled examples is then is given as an input to a learning algorithm. And then the algorithm does some computation over the sample and outputs a hypothesis function that is then used to classify new examples, for instance, new email messages. So for instance, for the spam detection problem, if the algorithm represents each message by certain features that, for instance, represent counts of certain keywords appearing in the message or not, then we should place each email message as a point in Rn. This is what we call the instance space. And then the algorithm might find a hypothesis, a classifier over the instance space that could be, say, for instance, a linear classifier. And this is what classic algorithms like perceptron or SVM would do. Okay? So formally, in these models, in the training phase, the algorithm first gets to see a set of labeled examples, for instance, labeled emails. We assume that these examples are drawn IID from some fixed but unknown distribution over the instance space. And we assume that they are also labeled according to some fixed but unknown target function. Okay? And the goal of the algorithm is to do some optimization over the given sample in order to find the hypothesis. And we want this hypothesis to have good small error with respect to the underlying distribution. And in particular, the notion of error that I'm going to consider for my talk is a classic 0-1 error or classification error loss, which is defined as the error rate of a given hypothesis H is the probability that our hypothesis H predicts differently from the target function on an example drawn at random from the underlying source. Okay, now the hypothesis H that we find comes from some hypothesis space, for instance, a class of linear separators. And the case where the target function itself belongs to the class is called the realizable case or the noise-free setting. And at the other extreme, the case where we make no assumption is called the agnostic case. Okay? So this is a classic formalism. And now in this model, models, the two main aspects that we typically care about are the following. So the first aspect is the computational complexity question or the algorithm design question. How can we automatically generate rules that dwell over the training sample, that dwell over the observed data? Okay, and this has been well studied, and a number of very interesting algorithms have been developed. Right? So this is one important question, the algorithm design question. Another equally important question in these models is the confidence bounds or sample complexity or generalization guarantees question, quantifying how many examples we need to see in order to be confident that the hypothesis that does well over the training sample will also do well in the future. Okay? And this is super well understood in this classic framework, in this classic setting. So for instance, I have on my slides a classic sample complexity statement that says that if the class of functions we are using has small VC dimension, finite VC dimension, So for instance, the class of linear separators in RD has VC dimension D. So if the class of functions we are using has small VC dimension, say VC dimension D, then D over epsilon times log 1 over epsilon examples are sufficient in order to be so that with high probability, in order to be confident that with high probability, all the hypotheses that have empirical error rate 0 will have true error rate at most epsilon. So in other words, what this statement is saying is that these many labeled examples are sufficient in order to make sure that a bad hypothesis, so a hypothesis of true error rate at least epsilon, will not going to fool us, because the hypothesis will going to be inconsistent with the data. Okay, so this is a statement for the realizable case. We can get similar results in the agnostic case in noisy situations, and we can get in fact even more refined bounds, and there is a lot of very beautiful work, that provides even tighter bounds based on more refined notions of complexity, like Radek macro complexity, and so on. So this is super well understood. Now, these questions in the classic setting, the algorithm design question, the sample complexity question, are super well understood. Okay. Now, as we have seen throughout this workshop, many modern machine learning problems involve massive amounts of data that is distributed across multiple locations. Okay, and in such settings, it is often the case that we would like to do learning over the union of these data sets. And moreover, we would want to do this with as little communication and as few rounds of communication as possible. Right? So for instance, we might have different hospitals with different distributions of patients. And our goal might be to learn a predictor to, say, classify a common misdiagnosis. Okay? Or as a different example, we might have various research groups that have collected huge amounts of data, say genomic sequence data, and our goal is to do learning over the union of all these data sets, again, without too much communication. Okay? So in these examples, in such settings, the data is inherently distributed across multiple locations. And each player, each holder, has only a piece of the overall data pie. And so clearly, in order to learn well over the combined distribution, the players must communicate. Okay, so basically, these settings bring to the forefront a very important communication complexity question. So, right? So in these settings, we have to understand the question of how much communication is needed in order to learn well. So in addition to the two classic aspects that I talked about, sample complexity and computational complexity, these settings bring to the forefront this communication complexity question. Okay, and they also emphasize other aspects like privacy, incentives, and so on. Okay, so this is precisely the setting that we study in this work. And formally, our model is as follows. So we assume that we have k entities. I'm also going to call them players. As usual, we have an instance space, like say Rn. And we assume that each player I has distribution di over the instance space, and the player can sample points from that distribution di. And these examples are then labeled according to some fixed but unknown target function. And in this setting, our goal is to find the hypothesis H that has small error rate over the mixture of these distributions, d1, d2, dk. Okay, so this is our goal. Now, as typical, again, I'm going to fix a class C, a finite VC dimension D. I'm going to call that D. As an example, you can think about the classic as being the class of linear separators. And for my talk, I'm going to focus on the case when K, the number of players, the number of entities, is much smaller than D, the VC dimension of the concept class. Okay? And again, and clearly, right, in these settings, the players must have to communicate in order to do well over the joint mixture. And they can do so by sending bits, examples, hypotheses, and so on. And in particular, in this setting, our goal here was to design learning algorithms that try to minimize the amount of communication needed to learn well. And the two aspects that we focused on, the two important parameters that we focused on, are the total amount of communication, which can be given by bits, examples, hypotheses, and also the number of rounds of communication, also known as the latency. Okay. Okay, and right, because I'm partly a theoretical computer scientist, I wanted to also make sure that in cases where we can learn the underlying class of functions by using efficient polynomial time algorithms, I also wanted to have polynomial time algorithms in the setting as well. Okay, so here is actually an interesting example to better understand the setup. Okay, so a simple, interesting example. So let's assume that we have two players and that one of them has the positive examples and the other one has the negative examples. And so in this case, the question is how much communication do we need to learn well over the combined data? So now that we want to do well over the combined data, not only to get a hypothesis HI, but as well over the distribution DI, because this problem would be trivial in this example. Okay. So this is our model, and in this model, we provide a number of general results, generic results on the amount of communication, the upper and lower bounds on the amount of communication. All right, so this is an overview of our results. Let me start by talking about two simple baselines. Here is the simplest baseline. So the first baseline is each player draws 1 over k times d over epsilon log 1 over epsilon examples and sends them to player 1. And player 1 does the learning. So in other words, he finds a consistent hypothesis. Now note that in this case, the total number of examples that get to player 1 is d over epsilon times log 1 over epsilon. So if these examples are really IID from the underlying mixture, then based on the sample complexity system that I had earlier, we would get good generalization guarantees. Now, this samples is not quite IID, in particular because on each distribution DI, we have the exact same number of examples. However, one can show that the usual double sample argument for the VC dimension theorem that I mentioned earlier still goes through. And we still get, we are guaranteed that the hypothesis that we output will have with very high probability generalization error at most epsilon. Okay? So in this case, the total amount of communication in terms of examples communicated is d over epsilon times log 1 over epsilon. And we can also get a similar result in the agnostic case. In that case, we'd have to send d over epsilon squared times log 1 over epsilon examples. And in both cases, that would be one round of communication. Okay, so this is the first baseline. Now let me mention another simple baseline for those of you familiar with learning theory and mistake bound. So it turns out that you can also have a baseline based on a mistake bound guarantee. So if you are looking at a concept class C that has a mistake bound of M, we can basically have one of the players, say player 1, run the mistake bound algorithm. So again, we're going to proceed in rounds. In each round, player 1 broadcasts its current hypothesis. If there is any player that has a counterexample, then that counterexample is sent to player 1. Player 1 uses it to update its current hypothesis. Otherwise, we stop if there is no counterexample. And it's immediate to see that based on the mistake bound guarantees, the total amount of communication in this setting, which is in terms of the number of examples communicated and also the number of hypotheses communicated, is M, where M is the mistake bound of the concept class. Okay, and in fact, if we can have each player run a shadow algorithm of the mistake bound algorithm, and then we would only have to communicate M examples. Okay, so basically, as opposed to the previous baseline that I mentioned, here there is no dependence in the communication. There is no dependence on 1 over epsilon, but the number of rounds of communication can be as large as M, where M is a mistake bound of our concept class. Okay, so basically just to summarize the baselines, on one hand, the first baseline has a linear dependence in D, the VC dimension of the concept class, and 1 over epsilon, while the second baseline has no dependence on 1 over epsilon, but can depend linearly in the mistake bound of the concept class. Okay, so these are the baselines. The interesting fact, the cool fact, is that it turns out that you can do much better. So in particular, we can do exponentially better in 1 over epsilon than the first baseline. So it turns out that we can learn any concept class C of finite VC dimension D by using only D log 1 over epsilon examples of communication. Okay, so, and actually we can achieve this by using a distributed boosting implementation. A communication efficient implementation of boosting, in particular of Adaboost. I'm going to describe it for Adaboost. Okay? And since this is a bit of, again, a broader audience, let me just mention that boosting is a famous algorithmic technique for turning a weak learning algorithm into a strong learning algorithm. And one popular algorithm is the Adaboost algorithm. So this algorithm takes as input a training set of labeled examples and a weak learning algorithm. And then it outputs an algorithm that it outputs a hypothesis that achieves arbitrarily small error rates. Okay, and the algorithm proceeds in rounds. In each round T, we construct a distribution dt over the training set. We then run the weak hypothesis algorithm on this distribution dt to get a new hypothesis ht, and then we use that hypothesis ht to reweight the examples for the next round. And in particular, what Adaboost does, so in the first round, first of all, we use the uniform distribution over the examples. I mean, it's just the first round. And then in round T, we create a new distribution for dt plus 1 for the next round by simply increasing the weight on the examples on which our current hypothesis ht was incorrect. So increase the weight on the hard example, and then we decrease the weight on on the examples on which the current hypothesis ht was correct. So we decrease the weight on the easy examples. Okay, so this is what Adaboost does. Now, the specific formula is written here. The details are not important. What is important is, and this is a key point, one of the key points that allows us to implement boosting in a distributed manner. So the key point, one of the key points is that at any moment in time, the current weight that Adaboost has on a given example xi depends entirely on the performance of the weak hypothesis generated so far. So depends entirely on h1 of xi, h2 of xi, h3 of xi. Right, so depends entirely on the performance of this hypothesis on our example xi, and also on some normalization factor that can be communicated efficiently. Okay, so this is a key point. And another key point is that in order to achieve weak learning, order of the examples are sufficient. So to achieve weak learning with respect to the distribution dt and each round t, order of the examples are sufficient. Okay, so given this, here is our distributed boosting implementation. So we proceed in round. At the beginning of each round, each player I sends to player 1 just enough examples so that player 1 can produce a weak hypothesis. So for instance, in the first round, each player sends only d over k examples. Then player 1 does the computation. He computes a weak hypothesis over the current distribution dt. And then player 1 broadcasts the current hypothesis ht to all the players. And then the players do the reweighting of the distribution locally. So they reweight their own examples by using the hypothesis ht. And then they also compute the total weight, their current total weight on their own examples. And then they send the total weight to player 1. Now player 1 aggregates these total weights in order to determine how many examples to ask from each player for the next round. And in particular, he's going to sample order of the examples from the multinomial given by these weights, essentially. Okay, so that's basically the distributed implementation of boosting. And basically, it turns out that this natural implementation leads to the following result. We can learn any concept class C, finite VC dimension D, by only using log 1 over epsilon rounds of communication. And in each round, we only need to communicate order of the examples. Okay, 10 minutes, great. Okay, and so, and this basically follows, so this fact follows from the fact that basically in Adaboost, to achieve error at most epsilon, we only need log 1 over epsilon rounds of communication. Here is a weak learning whose edge over the random guessing is a constant. So typical, the number of rounds, if you have a gamma weak learner, will be 1 over gamma squared log 1 over epsilon. Here gamma is a constant. So basically, we only need log 1 over epsilon rounds of communication to get error at most epsilon. Okay, and furthermore, in each round, we really communicate order of the examples. So, and some other low order bits, like some other low order terms, like we also have to communicate by how much our weights went up and down. We also have to communicate how many examples to send from each player. But in any case, all those are low order terms. So the dominant factor is order of the examples per round, log 1 over epsilon rounds. Okay, and this gives us the desired result that we can learn any concept class C, a finite ABC dimension D, by only using D log 1 over epsilon examples of communication. Okay, and furthermore, in the cases where we have, for the centralized setting, right, we have an efficient algorithm for getting a weak learning by only using order of the examples. In those cases, we also get a computationally efficient procedure. Okay. All right, so this result holds only for noise-free settings for the realizable case. For the case of the target function itself really belongs to my concept class. Okay? It's very natural to ask also what happens when you have noise. And it actually turns out that we have a generic result for the agnostic case, so for arbitrary forms of noise. Now, this result is not computationally efficient anymore. So, the computation, the amount of computation done could be very high. But what's interesting about it is that, again, if we have a class C, now in this case, if the class C is finite, we can again show that we can get a communication efficient protocol whose dependence on 1 over epsilon is exponentially better compared to the baselines. So basically, we can get a communication efficient protocol whose communication, it looks like log size of C log 1 over epsilon. And this is, again, exponential improvement over the baseline of D over epsilon squared log 1 over epsilon examples. Okay? And I'm not going to go into the details here. I'm happy to talk about this offline. Just the high-level bit, which I think is interesting, is that we got this result for the noisy cases by actually using a result that I had in a very different context, in the context of interactive learning with general queries. And so it turned out that algorithm for interactive learning with general queries, in particular with mistake queries or class conditional queries, was crucial to achieve this result in the distributed settings. Okay, and this points out, and I think Alec mentioned this in his talk yesterday, right? So this actually also points out that I think there is a very interesting high-level connection between active learning and distributed learning. So often, naturally, algorithms that are have a good sample complexity in an active learning scenario turn out to be useful primitives for getting distributed learning algorithms with small communication complexity. Okay, so I think this is interesting. And again, I'm happy to talk about the details offline of this result. Okay, so far I have talked mainly about generic results. So in the last 5 minutes of the talk, I also want to mention that for specific cases, like for specific concept classes, we can do even better in terms of the number of bits of communication. In particular, we could potentially remove the dependence on 1 over epsilon, or we could learn with fewer than D examples of communication. Okay, and a simple concept class, a simple case here is for the class of, for any intersection closed concept class, which means, so a concept class is intersection closed if it has the property that if we have hypothesis Hi in the class and we have hypothesis Aj in the class, then their intersection is also in the class. So it turns out that for any such class, if we furthermore have the property that each target function can be described compactly, like for instance, this is the case for the class of conjunctions, which is intersection closed, or the class of intervals on the real lines, it's again intersection closed. So if each function can also be described compactly, then it turns out that we improve over the baseline methods. Okay? And in particular, the result we show is that if C, the concept class C is an intersection closed concept class, when the class C can be learned with only one round of communication and K hypotheses of total communication. Okay, and the algorithm is actually not very complicated in this case. So very quickly what we do, so each entity I draws a sample as psi of size d over epsilon log 1 over epsilon. And then it finds the smallest hypothesis hi that is consistent with its own sample, and then sends that to player 1. And then player 1 outputs the smallest hypothesis H that contains each hypothesis Hi. Okay, and then the point is that that Hi, so that basically that each hypothesis Hi never makes a mistake on negative examples, because it's containing the target function, and so H never makes a mistake. And on positives, we can only, and on positives, the hypothesis H does only better. Okay. So this is a cute result where we can do, where we can do much better than the generic results. And in particular, just to give a quick, so for instance, a quick example for the class of conjunctions, which is intersection closed. So what the previous algorithm reduces to is that each player first finds the end, the bitwise end of its own examples, and sends that to player 1. And then player 1 just again does the bitwise end of its own examples, of those k examples that have been transmitted to him. Okay, so in this case, basically the amount of communication is order of k examples. Each example takes order of d bits to communicate, so in total get k times d bits of communication, which can be much better than what we get via generic methods, because in this case, the generic methods require order of d examples of communication, which end up being d squared. So on k is the number of players is much smaller than d, then we get an improvement over the generic methods. Okay? And let me just mention, and I'm not going to go into too many details, I'm just going to mention also that an interesting class from communication point of view is the class of parity functions. So this is a Boolean class of functions, the class of parity functions, say over the d-dimensional Boolean cube. Now it turns out that in this case, the generic methods require order of the examples of communication, so which means order of the squared bits of communication. And actually, in fact, if we use classic communication complexity lower bound, we show that this is needed. So this is needed if our goal is to do proper learning. So if our goal is to output a parity function, then order of omega of the squared examples of communication are needed. And this is true even for k equals 2. Okay, now what we show, I think it's kind of cool. In our work, we show that actually we can, if we are happy to do improper learning, so that means the hypothesis function is a more complicated hypothesis function, then we can learn with only order of d bits of communication. So which I think is kind of cool. Okay. And do I have time to go for the procedure?
You have 2 minutes left.
2 minutes left. Okay. So, okay, the very high level, okay, basically this result follows from the fact, from the observation that basically we can learn the class of parity functions in 2 ways. We can learn it, we can properly pack learn it. All we have to do is just given a data set S of large enough size, just solve a linear system. So we can properly pack learn it, but moreover, we can also non-properly pack learn it in the reliable useful model, which means that if we predict, we can either predict or say I don't know. When we predict, we'll be totally correct. And moreover, we say I don't know on most an epsilon fraction of the examples. Right? So, we can learn the parity functions in this model, in this reliable useful model, by simply just, again, draw a large enough set of examples. And the prediction function is if the new example, the test example, is in the span of the examples I've seen in the training set, I know how to predict because these are parity functions. Otherwise, I say I don't know. Okay, and basically using this fact, the distributive boosting, so the distributive procedure is as follows. Each player I basically pack lengths over its own distribution, so properly pack lengths over its own distribution to get a parity function hi. It also learns in the reliable useful model to get a rule GI, and then he sends his parity function HI that he learned in a proper way to the other player. And then each player then, in order to predict on a new test examples, the way they predict is if their reliable useful hypothesis predicts, it doesn't say I don't know, if it predicts on that example, they use it to predict. Otherwise, they predict using the other player's hypothesis HJ. Okay, and the key point is that we're going to have low error under the distribution DJ for the other player because HJ has distribution has low error on the DJ, and moreover, since GI never makes a mistake, putting it in front, it doesn't help. It doesn't hurt. Okay, so that's basically a very quick, fast argument of why this works. Turns out that the same trick can holds for any class that is that can be both properly pack-learned and learned in the reliable useful model. Okay, and this trick only works for k equals 2 when we have 2 players, and it's an open question to do it in general. Okay, cool. So now to summarize, to go back at a higher level. So basically in this work, we analyze communication complexity as an important fundamental resource when doing distributed learning. So we think it's as important as sample complexity and computational complexity. And we provide general bounds on the amount of communication needed to learn any concept class, a BC dimension D, and in specific cases we do even better. We achieve even better communication by using properties of the specific cases. And there are obviously many interesting open questions in this area, so I'm just going to mention 3 of them. So the first one is basically for noise-free settings, we have efficient algorithms. But for the case where we have noise, say any type of noise actually, we don't have efficient algorithms. So achieving efficient algorithms, communication complexity, right, polynomial time algorithms with good communication complexity, that's still an open question. Obviously, another natural question is doing the same thing for other learning tasks, like clustering. This has been mentioned a lot in the workshop. And another question is, so in our model, we assume that we are happy with communication protocols that have the property that for each player, they use a polynomial time algorithm and a polynomial sample. And then we wanted to minimize communication. But very naturally, we could try to trade off all these 3 different types of resources: sample complexity, communication complexity, and running time. Okay? Cool. Thank you.